Hey everyone, so this is the solution video for Worksheet 1.6. Here we're going to be talking about graphs of functions. And in number 1, we're given a function f of x is equal to 2x minus 3 and asked to identify a number of things about its characteristics and eventually trying to put together a sketch of what the graph would look like. One of the things that I'd encourage you to take note of when you have problems like these is to know what type of function you're dealing with and how you could classify it. In this particular case, we should all be pretty comfortable recognizing this is a linear function. And by recognizing the type of function that you're dealing with, some of the things will be known already. For example, we know what it looks like. It's a straight line. And also we know some certain things about domains and what we could expect from the graph. So knowing those is going to be helpful as we start to go through the class. We'll pick up more in terms of different types of functions and what we could expect from their graphs. But as far as this one goes, let's go ahead and start knocking out some of these parts that we wanted to address. So the domain of the function, let's start with that one. So one thing we can just kind of go ahead and put in our memory banks is that the domain of a linear function is going to be all real numbers. It's a straight line, it extends to positive infinity to negative infinity. So we can just go ahead and put that in there. The domain for f, since it's linear, will be the interval from negative infinity to positive infinity. And if you looked at the graph, either on your calculator or what we put together next, that would make plenty of sense. Okay, so next let's go ahead and identify these intercepts. Let's start with the y-intercept. Y-intercept is usually the easiest one to get. So the y-intercept. Now the nice thing about the y-intercept is if you ever want to calculate it given a function, we know that the y-intercept is going to be equal to our function evaluated at x equals 0, because that's where it's going to hit the y-axis when x is 0. So we can just take our function and evaluate it at 0, and that'll give us the value of our y-intercept. So in this case, what we end up with is y equals negative 3. So we know that our line is going to cross the y-axis at y equals negative 3. And as far as the x-intercept goes, the x-intercept, if we think about it in sort of the same fashion that we visualize the y-intercept, the x-intercept is going to be the point where we hit the x-axis. And the y value, or the value of the function at that point, will be 0. So this is really us trying to figure out what x value gives us a y value of 0. So what we could do is we can go ahead and we could take our function, whatever it may be, in this case it's 2x minus 3, set it equal to 0, and then solve for x. So in this case we would have, if we add 3 to both sides, we get 2x is equal to 3, and divide both sides by 2, and we'd get x is equal to 3 halves. So this is going to be our x-intercept. We also come to talk about this as a 0 of our function solution to the equation if we set it equal to 0. Okay, so we've got a couple of pieces here, and then we were also asked to sort of put together a table of points. The table of points is helpful if we are trying to understand what the curve looks like. The nice thing here is that we know this is a line, so we really only need a few points to get a good idea of what this is going to look like. So for our table, let's just go ahead and write down the intercepts that we've found so far. So in this table we've got our x's, and we've got the corresponding y coordinates. We know that when x is equal to 0, y is equal to negative 3. That's our y-intercept. And that when y is equal to 0, x is going to be equal to 3 halves, because that's our x-intercept. All right, so let's now address this graph. We know it's a straight line. We've got the intercepts, so this should be a pretty easy task. So if we set up a pair of axes. So we've got our x-axis here, we've got our y-axis here, which is just the values of the function at a given x point. So let's go ahead and plot these down. So when x is equal to 0, y is going to be equal to negative 3. and then when x is equal to 3/2, y is going to be equal to 0. So that point would be right about here. We've got 3/2. So I'm going to go ahead and plot those down in red. So here's one point, and here's another. So those are our two intercepts, and now we can go ahead and we could just draw our line through here. So this gives us a pretty good idea of what our curve will like, and this is the curve y is equal to 2x minus 3. Okay, so for number 2, we have a piecewise defined function that we're asked to graph. So again, we want to keep in mind piecewise defined functions, they've got that multiple personality type of thing going on, so we're going to probably see 3 distinct parts of this curve that we're going to need to put together. So I'm going to go ahead and treat them as such. Let's go ahead and start by putting up a set of axes to work with to get our graph. So here's our x and y axes, and we can see by the way that the domain is broken up here, if we look, that we've got a few kind of key points. 0 and +3 are going to be where the transitions occur in terms of going from one piece to the next to the next. So it'd probably be a good idea to go ahead and write those, to mark those down. So we've got 0 and then at 1, 2, 3. So we'll put that there as well. So we got x and we've got y is equal to f of x. So let's take a look at our pieces here. Let's start with the first one. So when x is less than 0, our function has a value of -3. Notice that that's not influenced at all by x. It's always going to be -3. So we have a constant function over this part of our domain. So we can go ahead and do is we can go ahead and say, well, I know that all the way from -infinity up to, but not including, so I'm going to put an open dot there because I'm not going to include it, on -3, this function has this is going to look like this. So that's our first part. Now the next part of our function right here, 2x minus 3, we've actually graphed this already, and this is a linear function, so we kind of already, we're lucky that we've got some of the pieces. What I would suggest is that if you need to graph a function, maybe find the 2 endpoints, so figure out what's going on here at 0, what's going on here at 3, and you can get a good idea. So I'm going to do that off to the side. So since these are the 2 points that break up our little subdomain here, I'm going to figure out, well, what would f of 0 be using 2x minus 3? Well, we'd have 2 times 0 minus 3, which would just give me a value of -3. So I know that down here, that's where the function is going to start, and then the other endpoint is going to occur at 3. So we'd have 2 times 3 minus 3, which would give us 6 minus 3, which would just give us a +3. So I know that on this other side of my line, 1, 2, 3, up here, that's where the end of the line is going to occur, right there. And again, it's an open dot because of the strictly, x is strictly less than. So now we also happen to know from our previous exercise that there's going to be an x-intercept right here at 3/2, so we can just go ahead and draw our line. Hopefully I hit that. Yay. And we've got our straight line. So this is our second point right here. The third part of our function is another constant function. So as long as x is strictly greater than 3, it's going to have a y value of +3. So we have another constant function going on here. So it would start here and extend off into infinity. So this would be our graph for our piecewise defined functions, and sometimes it's just a matter of recognizing what type of piece we've got, constant, linear, quadratic, who knows, and then getting the endpoints correct. So for number 3, we're looking at another sort of important characteristic of graphs that's good to keep in mind, which is this idea of symmetry. And symmetry can be determined by identifying a function as either even or odd. So if you probably remember from class, some of the things that we have at our disposal for determining whether or not a function is even or odd is that if a function is even, we will see that if we were to take our function f of minus x, so we've got our function f of x, we evaluate it at negative x, if it comes back after we simplify it as just our original function f of x, this is an even function. And about the graph, we would notice that this includes y-axis symmetry. So that's kind of a nice thing to recognize. So all of these would imply any other. And odd functions are recognizable if we took our function f, again, we evaluate it at negative x, and when the dust settles, what we actually have is a negative version of the original function. In that case, we would have an odd function, and this would imply that we have origin symmetry regarding our curve. So these are some good things when we're trying to get an idea of what the graph looks like. So in this case, we're given a function 3x squared minus 4, and we're asked to analytically determine whether it's even, odd, or neither, which is a strong possibility with functions as well. So let's go ahead and try this. So what we're going to do is we're going to check f of minus x and see what happens. And maybe we can make a conclusion based on that. So if we take f of minus x, that means we're going to have 3 times, we replace the x with the negative x, minus 4. And now we just go through and simplify it and see what happens. So if we take a negative x and square it, it's going to be negative x times negative x, which will make that a positive x squared. So this is equal to 3x squared minus 4. And this is a pretty simple one because right away we see that we've got the same function that we started with, which is f of x. So since for this function f of minus x is actually equal to the original f of x, f is even. And that's how we'd work out that one. And even though we're not specifically asked to do this in this case, since we know we have an even function, we know that this is going to display y-axis symmetry. So if we were to actually take a look at this graph, we know we've got a quadratic, which is a parabola, and it would turn out that this has a y-intercept at negative 4, and the curve would look like this. And we can see from that curve that definitely displays the type of y-axis symmetry that we associate with even functions. So that's another way that we could think about it. But in terms of what we did here in the red, that would be analytically determining whether the function is even, odd, or neither. Okay, so the last one we've got on this sheet is a bit of a doozy. But we're given a graph, excuse me, y is equal to f of x, and we've got a slew of questions that we need to answer. So let's go ahead and try and take these one by one. So for part A, we're asked to find the domain of f. So let's think about this. We talked about that the domain of functions, all the x values that the function uses, and we can also think about it graphically as the projection of the curve on the x-axis. So if we look at this, we're going to see that if we were to do a projection of this curve down to the x-axis, all of these points just getting thrown towards the x-axis. And even, you might be rightfully suspicious of this guy right here because there's a hole in the graph, but since this point exists here at x equals 2, this will also get projected down. So even though there's a hole in the curve there, that little point that's misplaced will take on that value. And what we see is that the entire x-axis in between these 2 points, positive 4 and negative 4, are filled up in our domain. So we could highlight that projection as going from negative 4 all the way out to positive 4, and that would be our domain. So we can go ahead and say that the domain of f is going to be all points from -4 inclusive with the brackets to +4 inclusive, and that would be our domain. So for the range, we can think about this as our projection on the y-axis of our function. So let's go ahead and take a look at that. If we were to look at our curve and project all of these points over to the y-axis, we just keep pulling everything over, sort of cast that shadow of our curve over to the y-axis. We'd start down here at -5, and all of these points in here, then we get to the origin, and everything, it's casting this shadow along the y-axis. The only thing we have to watch out for here is when we get to 5. Since this is an empty point, technically we never really get 5 in our range. So we're only looking at a range that includes points from y equals -5 inclusive to +5 not inclusive. So if we were to go ahead and put together the interval notation for our range, we would say we're going from -5 all the way up to +5, but since we're not including +5, we'll use a parentheses for that. Okay, so that takes care of the range question. Now we've got to evaluate our function at -2. So when x is equal to -2, what is the value of our function? Well, let's see. We're going to go to x equals -2 right here. Now, we want to figure out what the value of our function is at x equals -2. And we see that when x is equal to -2, our function has a value of -5. So because that's the point that we're looking at there, we're going to go ahead and take that as our value. So this is going to be equal to -5. So when x is equal to -2, y is equal to -5. Okay, so part D, solve f of x is equal to 4. Now this is kind of the reverse of what we just did. This is saying, well, we need to know for what value x is y equal to +4. So let's go ahead and write that out just so we're clear. So for what x is y, basically the value of our function, equal to +4. So that's what we want to figure out. So let's go up and take a look at our curve. So y equals -4. Let's go ahead and locate that. So that's right here. So for what x values will we get there? Well, here's one of them. You know, one thing you could do is you could draw a horizontal line through there and say, okay, well, anywhere that this horizontal line hits my curve is where my function is going to attain a value of 4. And it happens right here, and it happens right here. And these points are x equals -1 and +1 and x equals +3. So what we can conclude here is that when x is equal to +1 or x is equal to +3. So those are really our answers here. So those would be our solutions. And again, we could see this another way if you're not quite convinced. If you were to calculate f of 1, or if you were to calculate f of 3, meaning what's the value of this function at 1 and at 3, in both of these cases, if we were to look up at the graph, the value of our function at those 2 points is 4. And that's exactly what we were asked to look for. Okay, so next we're asked to find the x-intercepts, if they exist. So we want to know, when does this curve hit the x-axis? All right, so let's clean this up. So we're looking for our spots along the x-axis where this curve is going to cross. And we can see this happen, it looks like at 3 different places. So one right here, one right here, and one right here. This is where we're hitting the x-axis. So each of these points has a specific x-coordinate and a y value of 0, since it's on the x-axis. So let's go ahead and write those. So the x-intercepts exist when x is equal to -4, when x is equal to 0, and when x is equal to +4. And if we were asked for the specific coordinate points, then we could write this as -4, 0, 0, 0, or +4, 0. So either of those would be, a fine way of expressing these x-intercepts. So for f, we need to find the y-intercepts if they exist. So let's go back to the graph and see what we've got going on here. So we're looking for points where we hit the y-axis, and it looks like it really only happens right here at the origin again. So it's not only an x-intercept, but it's also the only y-intercept that we would have. So this is going to happen at y equals 0, and if we wanted to write it at a coordinate, we have the origin 0, 0. Note that functions are never going to have more than one y-intercept. If they did, then it would fail the vertical line test. So we would never run into that situation. Sometimes there isn't a y-intercept, but for functions, there's never going to be more than one. Okay, so for part G, we want to find the number of solutions to f of x is equal to 1. So this is kind of like what we did in D. We're wondering, how many times does our function have a value of a y value of +1. So we're looking for when y is equal to +1 here. And looking at this, we go to +1, and I'm just going to go ahead and draw a horizontal line through there. So anytime our function hits that line, it's a change of value. So it looks like it does it once here and once here. So in this particular question, if we're being asked to find the number of solutions, we've got 2 of them. So there exist 2 solutions. And those are, something like maybe a fifth and then 3 4/5. Who knows? We'd have to estimate that. But that's what we would say there. Okay, so for part H, we're asked to list the intervals where f is increasing. So increasing is sort of an intuitive thing to see from a graph. We want to know when it's going up. So the graph, if we think about it, if we start over here at x equals -4 and we keep moving, the graph is just decreasing as we go along here. Then once we get right here, it's a turning point, and our function begins to increase, and it increases all the way up to this point right here. So on this interval right here, from -2 all the way up to +2, our function is increasing over this entire little area. So from -2 to +2. So we would say that it's increasing from -2 to +2. And since the function is got a hole right there at +2, we're not going to include that. And the authors for these increasing, decreasing, they will include the point where it changes from increasing to decreasing, and they use the bracket. So this is the notation that we would use to express this increasing interval. The other 2 intervals that we've got, it's decreasing. So it's decreasing to the left of that interval, and it's decreasing to the right of that interval that we just highlighted. Okay, so next we're asked to find any local maximums. Now local means as opposed to an absolute. It just has to be a max relative to the points around it. And if we look up here and we're looking for local maxes, so the first one that might jump out as a possibility is this high point here, but unfortunately it's not defined there. So this one is not going to be included as a local max. However, and this one might be a tough one to see, right here at -4 we actually have a local max, because this point right here is larger, has a larger y value than any of the other points close to it or around it. So relative to the points around it, that point is a maximum. So and this is the point -4, 0. So the way that we could express this is we could say that that the function has so f has a max value, or let's go ahead and call that a local max to be specific, It has a local max of, and here we specify what the y value is, what the actual value of the function is. So it has a maximum value of 0, and now we indicate when that happens by saying when x is equal to -4. So when x is equal to -4, we have a local maximum value of our function at 0. And then we're also asked to find any local minimums. And if we go back up here to our curve, we clear up this mess. We're looking for points that happen to be sort of minimums with respect to the points around it. Well, here's one right here that we can actually include that point because it's defined, and kind of like the last time, we're going to include this as a local min, because with respect to the points around it, that point right there is a minimum value. This point is also a minimum value. So the mins we're going to use will be 4, 0, and we'll also use -2, -5. So now we've got to write these up. So f has a local min of, we'll do the first one, of -5 when x is equal to -2, and f has a local min of 0 when x is equal to +4. So those 2 points right there will serve as our local min. Now it also happens to be the case that this min right here is also absolute, but they only asked about local, so that's all we needed to give them. Okay, so that does it for this video, and I'll see you all in the next one.